is Jeff Williams. I'm from XM Instruments, and I'm trying to convince you that mass spectrometry is still sexy. So it's a tall order, I know. So basically, I'm going to be talking about a new technique that we've developed at XM Instruments and how we're bringing this to additive manufacturing. So I guess let's first start about why do we care about chemistry and additive manufacturing? You know, it's a completely different environment than we've ever been in before, where we're building the material properties as we're printing the part, right? So if there's any sort of chemical defects that's happening in the printing processes, these are going to have big implications for your part process control. And currently, whether you want to test for corrosion resistance or heterogeneity, material properties, or just QA and QCing your parts, the best way to do solid sample analysis is to still digest it in a bunch of acid, do a bunch of dilutions, go through 3 different instruments in order to get the whole periodic table. So you need 3 analytical instruments, you need a lab that looks like this, that still looks like it's out of 1975. You have a bunch of helium and argon tanks, you have fume hoods, you know, it's a mess. And I wanted to completely change this. And even if you wanted to use external labs right now, at best, if you want to do the whole periodic table, you're looking at up to $1,000 per sample and 4 weeks of turnaround in order to get the chemistry you need to, whether that's QA/QC for your production to get your powders to customers, or whether it's just on your R&D cycle. So we've taken that, we have a new technique which offers the entire periodic table in, instead of 4 to 6 weeks, 4 to 6 minutes for full chemical analysis. You can go see it over there at our booth, sitting on the table, sits on a desktop, touchscreen interface. You don't have to be the analytical chemist. We can be the analytical chemist for you. You can get the data you need and move on with your life. And this obviously is saving on in-house instrument costs. You don't need to build an entire lab facility. It's just one instrument. And this increases the R&D turnaround time for developing new powders, for QA/QCing powders to get them out to your customers. We wanted to change this because where I came from, I was in a lab that looked very much like this lab that hasn't changed since 1970, and where the best way to do solids, whether it was a powder or a solid, was to do a bunch of acid digestion. So really briefly, I'm not going to go into too much details of how the technique works. If you want to nerd out with me more later, we can go into it, but it's essentially a laser-based technology. You know, we like to say that we're doing chemistry at the scale of printing. We have one primary laser that removes about 10 to 100 nanometers of material and creates a neutral particle cloud. You can imagine this is like, you know, drilling into concrete, you kind of get this spray off. We take a secondary laser and we're ionizing that particle cloud. We're stripping off electrons and now they have a charge. We can then interact with these ions and basically kick them really hard. And if you kick an ion really hard, they're going to move as a function of their mass. So light elements go very fast, heavy elements go very slow. So it's like kicking a soccer ball or a bowling ball. One goes a lot faster than the other, one hurts a lot more. But you end up with something that's called a mass spectrum. So basically the x-axis down here is mass, but it's essentially equivalent for time. So our soccer balls, our light elements are going to be on the left-hand side, our heavy elements on the right-hand side. And what's unique about our technique is the way that we do the ablation, the ionization, all of that. We get every element, and we get it what's called isotopically correct. And it's okay if you haven't heard the word isotope in a while, but basically it allows us to verify that every element actually is that element. So again, going back to you not being the analytical chemist, us being the analytical chemist, you can see boron, carbon, nitrogen, and oxygen here, all of the light elements that are generally done with a separate instrument. We get those at the same time that we're getting tungsten all the way out there. So lights to heavies, all isotopically correct. So very easy to use. And this figure just kind of shows that very quickly, that basically anything that's colored on this periodic table, we can analyze. The color coordination says how sensitive are we to each of the elements on here. We can go down to parts per billion level. Generally, we tend to operate at parts per million because that's what people in this space tend to need a lot of the time. But we can get to very low limits of detection across the periodic table. We're doing all of the light elements, whether it's boron, carbon, nitrogen, oxygen, and everything on the table. We obviously don't do noble gases, but we can analyze everything. And I'm sure a lot of what you're wondering as well is, yeah, but do you get the right answer? Is this actually quantitative, or am I losing something by not using these older techniques that have been around for so long? So let's just go through some powders that we've run. You know, a lot of what we're trying to do in this space is simplify powders analysis. So whether this is steels, aluminums, coppers, we can do it all. And the first part to this process is simplifying that preparation. Instead of doing a bunch of digestion and nitric and, you know, different solutions and column chemistries and then running it through a plasma, all you need to do is take the powder, about 1 to 4 grams, put it into a die set, and put it on a hydraulic press. And with a matter of a few minutes, you have a puck that looks like this. So these are 13 millimeter pucks that we like to use, very small. And you know, there's a little bit of variance of how we press it depending upon the material, but pretty much everything can be pressed. Sometimes we add a little bit of binder if it's, you know, something that's very difficult, like a chromium powder. We'll add a little binder, but it doesn't really affect our analysis at all. So really simplifying that sample preparation process so that we can do this very quickly. You then load up these pressed powders, or you can even see here, there's actually some test cubes that people have run, again, showing we can do solids or powders. Anything solid we can analyze. This is one of our sample holders that holds 16 samples, but we can customize this for whatever your needs may be. The total area that we can analyze by this technique is about 3 inches by 3 inches. So we have a stage that can move around in both the X, Y, and Z dimensions. And so 3 inches by 3 inch X and Y, about 1 inch in Z. So we have a large volume in which we can operate in and increase throughput. And again, going to simplifying it, if anybody of you have used any analytical instruments, you know it's still based in like Windows 1995 UI experience, and we wanted to modernize that. We wanted to take what it's like to use an app on your cell phone and make it the same experience for an analytical instrument. So this is the actual screen that's used to do analysis. It's a touch screen. You can go touch it over there if you want to. You're loading up your samples. We just threw a bunch of things in here. You can do line analysis, you can do spot analysis, or you can actually do chemical maps, which I'll show you in a little bit. You can actually get resolution X, Y, and Z of your chemistry. And so you can do heterogeneity studies of your powders. So you choose your spots, whatever you want to do, you press go, and we are the analytical chemist from here on out for you. Again, every spot that's analyzed, we end up with this thing called mass spectrum. We process that data, and let's say you wanted to do a map. You wanted to actually look at the chemistry on the surface versus below. You wanted to look for heterogeneity in your powders, actually analyzing individual particles in your powder. This is a study where we wanted to look at the surface. We wanted to see what's the oxidation and contamination on the top versus the bottom. So we did a stripped down analysis. So the layer 1 is the top layer, and layer 2 is the layer right below that, and we can keep going down. So this is useful in coatings. This is useful in titaniums that oxidize very quickly. You can kind of see what that affect's like. And you can also look for chemical heterogeneities as well. You're seeing this, you know, this red blob on the right-hand side this customer didn't expect. So that was, you know, something fun that came out of this. But just an example of the resolution and what this technique can offer you. And something I want to that's powerful here is that each one of these pixels is about 11 microns on this sample. We can go down to 1 micron or up to 150 microns. And every pixel on this image has a mass spectrum on it. And you don't need to know ahead of time what you're analyzing. So a lot of times with traditional techniques, you need to know, okay, I'm analyzing a stainless, I need to look for chromium, molybdenum, iron, nickel, whatever it might be. So you tell your external lab, hey, I care about these 8 elements. But then 8 months down the line, you're starting to get all these issues, and you're wondering, is this a vanadium issue? Is this a manganese? What's causing this problem? If you didn't analyze those elements, that data is lost forever. With our technology, you get every element whether you like it or not. So you can always go back and look at everything you want to at every pixel. So going from this mass spectrum to 500 parts per million, 3 weight percent, how do we do that? And also, how do we simplify that process, improve robustness? Well, there's something called matrix effects in the industry, and basically that means that if I wanted to analyze this cup and only this cup for some chemical composition, I have to have a standard that perfectly matches this cup, right? And if I brought in anything that's outside of a variance of what I know about it already, it would be called a matrix effects, and I could no longer quantitate anymore. I need a new standard. So we wanted to prove that we're more robust than that. So we did a garbage can experiment. We said, where does it break? So what I'm showing here is what's called a calibration curve. So we took a bunch of things that were known. We threw powders in yellow. Blue is solid samples. This is pure iron end members to stainless steels. So a huge change in matrix, right? And we plot them all in the same curve. We're insensitive to whether it was a solid cube, whether it was powders that were pressed, whether it was low nickel, high nickel, whatever it was, we're able to quantitate anything within the spectrum of an iron material. And I know that if you're not analytical chemists, it's not as sexy to you as it is to me, but I promise this is really cool that we can do this. And really the takeaway is that it's very robust analysis. You can trust that we're giving you the right answer, even if the standard was a little bit outside of that value. So if you had a standard in there that was 10 weight percent, but then you're measuring something on 5 weight percent with your unknown, in traditional techniques, you wouldn't be able to quantify that because it'd be too much outside of the range. And with our techniques, we have very high dynamic range for quantitation. And independent of if it was a powder or a solid, going back to standards, this is a big problem, as we heard yesterday in this industry. Same thing on standards for chemistry, where especially in powders, it's a major issue. Maybe there's other standards that existed for more traditional techniques in the past that are solids, but now you want to do a lot of powders. And with other technologies, those standards don't apply one-to-one. And so we can get around a lot of the supply shortage of standards by utilizing more traditional standards for analyzing powders. So we'll kind of go through some data of showing like solids versus powders, steels, aluminums, titaniums, and I want to leave a lot of room at the end for questions. So what you're going to see here is basically gray line is the certified reference material and blue line is the data that we gathered. This is for a solid curve and this is for a powder. Basically, we're always getting the right answer within error of reference materials, and these were actually quantitated using that garbage can experiment that we did. So it didn't matter what we threw at it, we were getting the right answer for other unknowns as well with the same quantitation curve. So, and also I should point out here that the left-hand side is in weight percent for the major elements, and the right-hand side is trace elements going down to 50 parts per million there for cobalt. And what you're also seeing is nitrogen we're quantitating accurately. So if you ever had to do these sorts of experiments before, you know that your oxygen, your nitrogen, your carbon, that's generally done by a different technique than the things that are quantitating your chromium and nickel. So we're getting the whole periodic table on a huge dynamic range from 18 weight percent down to 50 parts per million. We can do everything in the same analysis. So that was stainless steels. We've done titaniums as well. Again, oxygen, super important for titaniums and understanding how that changes. We've done aluminums, 2024s, and also validated this with external labs. We've done coppers, we've done Inconels, both all of the series of Inconels now. We pretty much have done all of the powders within additive manufacturing, and we want to keep learning and keep proving that we can become the de facto tool for this space. And so please come check out our booth and come talk to us if you have other applications. So just going to conclude a little bit early here by just saying that this technique, Lolitoff, or the mass box, is a new technique for elemental characterization of additive manufacturing materials. Whether this was the powder or the solids, we can do it all very easily. We can fit a ton of samples on here for high throughput analysis, and we can do full chemical characterization. We're less dependent on specific matrix matching, which means that if you are developing a new powder or a new steel, whatever it might be, and your labs don't have certified reference materials, we're not as sensitive to that. It doesn't matter for us. We can still quantitate it, we can still speed up your R&D, and we can still do all of the work you need done to develop this material and get it out to the world. We have consistency across powders and solids, and it's minimally destructive, basically non-destructive. We're removing 10 to 100 nanometers worth of material. So for all intents and purposes, it's non-destructive. And we can do this in 2 or 3 dimensions. So if you're trying to analyze, this was powder where we were looking for hot spots of a certain element, and we were able to do basically a heterogeneity test of did this provider actually provide us with a homogeneous powder to make a solid part, and they didn't consistently. So we were actually able to show that by chemically mapping this powder. So with that, again, I'll end early and leave lots of room for questions. Thanks. So the company was founded about 5 years ago, but we've actually are just, this is our first year of production. Yeah, we're really trying to, break into this additive manufacturing space and become the de facto tool, to make this a lot easier, to bring more of this chemistry in-house when there is a big focus on it in this space. So, yeah, please come to us with application ideas, and we want to learn what the problems you guys are facing and what we can do to make it better.
On one of your bar plots, maybe the one for the solid powder seemed like one of your error bars was executing past the value.
Yeah, and that comes down to, again, that was basically that line that we made with a bunch of different types of matrices. Those were quantitated from that line, and so the errors are a function of where it is in that line. So that element was very far off of where the known was for that, so the error was higher. So if you wanted to bring the error down, it's a matter of like finding a standard that's closer represented. So our errors are not reproducibility. We get the same answer every time, but it's an accuracy error that we report. So we don't try to do any shiesty things of like, yeah, it's 1%. It's like, no, it's taking into account every error that's accumulated in the machine.
So if you're getting something printed by an outside company and you want to make sure that it's what you're paying for, would you suggest doing the analysis on an actual part or like on a coupon?
Yeah, great question. So yeah, the best way to do it is to do a coupon. So especially if you're going to do like material testing as well or mechanical testing, let us throw the coupon in, do an analysis on it first, and then go do your testing right after that. So it's all on the same piece as well. Yeah, so it goes right into the workflow. Awesome. All right. Well, come over and check out our booth and come touch it. Thanks.